So let's start off our relativity problems by doing a couple on time dilation. So for time dilation, we have just one equation, delta t is equal to delta t0 divided by the square root of 1 minus v squared over c squared. So v is the speed at which the object's moving, so in this case it's a spaceship. So we've got v is equal to 0.985 times c. And we're told that we have the spaceship is moving past Mars. The signal light on the Martian surface blinks on and off. The observer on Mars measures that the light was on for 75 microseconds. That's 75.0 times 10 to the minus 6 seconds. And let me just call this delta t for Mars. And we want to know what's delta t for the spaceship. And in part A, it asks who measures the proper time. And so we're going to have to think about that before we can put it into the equation. So which one of them is delta t, and which one of them is delta t0? So delta t0, that's the proper time. And the proper time is measured in the frame in which the two events occur at the same location. So in which frame do the two events occur at the same location? Well, if I draw a quick little picture over at the side. So here I am on Mars. So the person standing on Mars, they see the light go on and off, and they see that happen at the same location. The spaceship, my rocket ship, he might be over here when he sees the light go on, and then he's going to have traveled all the way over here by the time he sees it goes off. So for the person, the spaceship is at different locations. The person on Mars is at the same location. So the person on Mars is the proper time, and the person in the spaceship is the moving time. So delta t on Mars, that's delta t0. Okay, so we know delta t0. We know v, and so we need to figure out what's delta t for the spaceship. Right, so it's going to be delta t0 over the square root of 1 minus v squared over c squared. And now we're just going to plug this in. So delta t0 is 75 times 10 to the minus 6 seconds. And then the denominator, we're going to put 1 over the square root. Now v is equal to 0.985 c squared divided by c squared. So you can see I've got a c squared over c squared. So those c's are going to cancel out in there. So this is actually comes out to be delta t on the spaceship is equal to 75 times 10 to the minus 6, or 1 over the square root of just 1 minus the denominator disappears, and just have 0.985 squared. So I get the denominator comes out to be 75 times 10 to the minus 6 over 0.1726. And so I get 434.6 times 10 to the minus 6 seconds, or 435 microseconds. Okay, so we've got the one equation. The only trick to it is to figure out which one is the proper time and which one isn't the proper time, and then you know which to put in. All right, let's do one where we take that equation and now we rearrange it to find the speed. All right, so now I have a positive pion lives on average 2.6 times 10 to the minus 8 seconds measured in its own reference frame. So it lives and dies in the same reference frame. So that's going to be our delta t0. It's 2.60 times 10 to the minus 8 seconds. And if we take that pion and we put it in an accelerator so it travels really, really fast, the person who's in the lab will measure that it lives longer, that it lives 4.20 times 10 to the minus 7 seconds. Okay, so we want to know what speed is it traveling. All right, so what we know is that delta t is equal to delta t0 divided by the square root of 1 minus v squared over c squared. That's the only equation we have. So I want to get the v out of that. So I'm going to have to do a whole bunch of math, a whole bunch of algebra to get it. So let me first, I'm going to multiply that up to the side. I'm going to show you all the steps in the math. It's going to be delta t times 1 over v squared over c squared, square root, equals delta t 0. Now let me get rid of, so if I want to get the v, I first have to get the term with the v in all by itself. So I'm going to just divide by delta t on both sides. So let me put some arrows in here so you can see what I'm doing. So the next thing I'm going to do is divide both sides by delta t. So I'm going to get 1 minus v squared over c squared is equal to delta t 0 divided by delta t. And I can put in my numbers now, right? I've got delta t 0 and I got delta t. So I've got 2.6 times 10 to the minus 8 and 4.2 times 10 to the minus 7. I get 0.0619. So I've got, copy that down, 1 minus v squared over c squared is equal to 0.0619. All right, so now I still have to work on getting that v out of there. So first thing I got to do is let's get rid of that square root. How do I get rid of the square root? I got to square both sides. Okay, so 1 minus v squared over c squared is what I get if I square the square root. On the other side, I square 0.0619, and I get 3.832 times 10 to the minus 3. Okay, now I want to get this term by itself. So what I can do is I can add v squared over c squared to both sides. Let me do this just step by step so you can see all the math. So plus v squared over c squared. Then to get the v squared by itself, I'm going to subtract that 3.83 term to the other side. All right, so now I've got 1 minus 3.832 times 10 to the minus 3 equals v squared over c squared. And that is 0.99617. It's pretty close to 1, is equal to v squared over c squared. All right, so now I'm getting close. So I've got now v squared divided by c squared. So to get it by itself, I'm going to multiply both sides by c squared. Okay, so now I've got 0.99617 c squared is equal to v squared. All right, so now only one more step. To get v, what am I going to do? I'm going to take the square root of both sides. So I get v is equal to the square root of 0.99617 times the square root of c squared is just c. So v is equal to 0.998 times c. So it's a lot of algebra, but if you follow it through step by step, you shouldn't have any problem.